Hi everybody, so in this video I'm going to be covering exercise 9.3, specifically some of the questions that you have from this exercise. And first is number 4, and it says an object moves along a line, so it's the object is moving along a line, such that its displacement, s meters, so let's underline along a line because that's very important. So its displacement s meters at time t seconds from the origin, so it's from the origin, is given by this function here. A, find an expression for the object's velocity and acceleration in terms of t. So I'm sure that all of you did this easily because you know that velocity is the first derivative of displacement. So you're going to get that it's going to be 3t squared minus 8t plus 1. And the acceleration is just going to be the second derivative or the derivative of velocity. So it's going to be 6t minus 8. Okay, so now here we are on part B, and it says for the interval from -1 to 3, sketch the graphs of the displacement time, velocity time, and acceleration time graphs of separate sets of axes vertically. Okay, so basically this just means plug these into your graphing calculator. And of course, when you do it in your graphing calculator, remember to do it in terms of x. Or you can just do it manually as well, but it takes more time. So if we graph them in the calculator, we have the displacement, we have the graph for velocity, and then the graph for acceleration. So notice that displacement is cubic, velocity is a parabola, and acceleration is linear. And that has to do, of course, with the fact that of derivation, doing the derivatives. So now let's move on to part C. Okay, so for part C, they say for the interval from -1 to 3, find the time at which the displacement is a maximum and find its value. So let's recall that the displacement formula or function is s of t is equal to t cubed minus 4t squared plus t. So there's two different ways we can do this. We can graph this and find the maximum, which is what I'm going to show you next. And then there's another way, which would be using the velocity formula because it's a derivative of displacement. So velocity is equal to 3t squared minus 8t plus 1. And if we equal this to 0, we should be able to find the maximum. Now, the problem here is that we can't really do this by inspection because notice that this is 3t times t, and then there's no way we can get -1 times -1 or 1 times 1 and somehow get -8 here in the center. So we can't really do this easily. We could do it using the quadratic formula, but that's too lengthy and we're going to end up using the calculator anyway. So in the next part of the video, I'm going to show you how to do it using the GDC. So the easiest way to do this is by plotting in your graphing calculator the function for the displacement. But of course, it's going to be in terms of x and not in terms of t. So we would graph x cubed minus 4x squared plus x. So remember that we do this here where it says y equals x. And then we just, once we plug it in, we just hit graph. And there is your graph. Now here we have to be careful because the interval is from -1 to 3, so we should mark that. So no, this would be -1, so we're interested in the function from here to 3, to there, right? So that's all we're interested in. So notice that the maximum has to be somewhere here, and I'm going to put a circle on it. And the way to calculate it using the graph is simply by using the keys here. So you notice that on the trace button here on the top right hand corner, second one right to left, it says trace. On top of that, it says calculate. So that's what you're going to use. You go second function, calculate, and you have this option number 4, which says maximum. So hit that, maximum, and then it's going to ask you for a left bound. So a left bound means move the cursor to the left of where you think the maximum is a little bit, and we hit enter. Then it's going to ask for a right bound, and we're going to move it a little bit to the right of where we think that maximum is, and hit enter. And then it's going to say guess. You hit enter again, and there you are. So you found the maximum or the time, right? Because it's in terms of time. The time at which it reaches the maximum would be at t equals 0.1315 if we want to round seconds, and the maximum displacement will be of a mere 0.0646. Okay, so I'm going to show you the second method of solving this problem, and it is using the app called Polynomial Simultaneous Solver, which is app number 9 under the apps button. So hit number 9, and you want to use number 1 because it's the polynomial root finder. So let's do number 1 and order 2 because it's quadratic. So notice that here it says next, but you want to hit the button that says graph, which would be right under next on the screen. So there you go. And notice that it gives you the chance to put in the coefficients. So let's recall that the function we're talking about is the one for velocity, right? So velocity is, we said, equal to 3t squared minus 8t plus 1. So we have to put in the coefficients of this equation. So let's start with the first one, and the first one is 3, so we just type in 3, and then you hit enter, enter. Oh, wait, it's minus, so I have to go back. This is minus, so type in minus, and then we type in 8, enter. Oh, what happened? No, I got to type it again. So minus 8, enter. There it is. Plus is fine, and then 1. Okay, enter that. Equals 0, that's fine. So now we can just click on graph, which is really solve. So notice that it has two solutions, but we already know from the previous way of doing it that this is the only solution that we're interested in. And this is another one. This is probably a minimum in that same interval, or where this equals x. So that means where this would cross, where it would cross the x-axis, right? So how do we find out which one is the correct one? Well, we would put these numbers into the original function and see which one gives us the highest value, because they are obviously both within the interval between -1 and 3. Okay, so here we are in part D, and it says for the interval between -1 and 3, find the time at which the velocity is a minimum and find its value. So we can do this in two different ways. First, I'm going to show you how to do it on the graphing calculator and then manually. Okay, so for the calculator, remember that we hit on the button that says y equals top left corner, and we plug in the function for velocity in terms of x. So once we have that, we graph, and there it is. Notice that it is a parabola that goes upward, and we have to find this because the time interval we're interested in is, of course, only between -1 and 3, 1, 2, 3. So the minimum we're interested is here. For that, we do the same thing we did last time. It's simply use the trace function or use the calculate function that is on top of trace, but in this case number 3, which is a minimum, and then left bound, so we go near where we think the minimum is, and click enter. Right bound, we got to move a little bit to the right of that, click enter, and guess, yes, enter, and there it is. The minimum occurs at time 1.333, so 1.3333. And it's the maximum velocity, or the minimum velocity, excuse me, would be -4.3. Okay, so how do we do this manually? We saw how to do it on the graphing calculator. Now manually, remember that the velocity function in terms of time is 3t squared minus 8t plus 1. And the derivative of this is the acceleration, which is 6t minus 8. So we can find the minimum or the maximum of a function when its derivative equals 0, right? So let's just go 6t minus 8 equals 0, and we solve for t. So we're going to get 6t is equal to 8. So t is equal to 8 over 6. So t, I'm going to write over here to the left, t is simply 4/3. And that is, of course, 1.3333, right? This 3 goes on forever. Um, so this would be the time at which there is a minimum. And that minimum velocity would be just plugging in the value 1.3 into the function. And this gives us approximately negative 4.3. Okay, so here we are on part E, and it says describe the motion of the object during the interval between -1 and 3 accurately. So the first thing we have to remember is the fact that they said at the beginning that this object moves along a line. So the object is moving along a line. That means it's only moving right or left, right? And if it's right, it's a positive displacement. And if it's left, it's a negative displacement. Luckily, if we take a look at the acceleration, remember the acceleration graph was linear, so that means the acceleration is constant and we don't even have to bother describing the acceleration. All we have to do is describe velocity and, well, this is the acceleration graph, but all we have to do is describe velocity and displacement. So I put both graphs on the same set of axes in order to understand how to describe its motion and its velocity. So the red graph is the displacement. So notice that if we look at the red graph, first it's going up, right? So as time increases, so does the graph. That means it's moving to the right. So we would start by saying moves right, moves right. And what's going on with the velocity? Notice that the velocity is working against the displacement. As the displacement increases, the velocity decreases. So we would say moves right with decreasing velocity. So moves right with decreasing velocity. Now notice that the velocity gets to 0 at this point, which is, of course, where the slope of the graph is 0, but the slope of the displacement graph is 0. So notice that that means that it stops. It stops, the object stops, and then turns left. So then turns left, so let's say stops, not stopped, stops. So stops, turns left, and what's going on with the velocity? Now notice that the velocity is still negative, right? It's going down, but it's working in favor of the displacement. The displacement is to the left and the velocity is negative, but that is an increasing velocity because we're moving to the left now. So it turns left with increasing velocity. So it turns left with increasing velocity. And then notice that the velocity, which is the blue chart again, it's increasing in the negative, and then it sort of turns around. It doesn't stop, but it starts slowing down. It slows down. Notice that it slows down. So it turns left with increasing velocity, then slows down, right? It slows down because the velocity is slowing down. Notice that the velocity is slowing down, and then it goes towards the positive, which means it's decreasing in the sense of the negative displacement. It's going against the displacement until it stops. See, it slows down. And where does it stop? Right here, right? Right here. So then slows down, stops, stops, slows down, stops. And then, so we're talking about the displacement. So notice that it's going towards the left, velocity slows down, stops, and then turns right again, right? Stops, and then turns right, turns right. And you have to say again that the velocity after it turns right, notice that the velocity is positive now. And because the displacement is towards the right, it works in its favor. So we'd say turns right with increasing velocity. And that's all we have to describe because it's only in that time interval. Okay, so next is question number 9. And it says the curve y equals x to the 4 plus ax squared plus bx plus c passes through the point -1, -8. And at that point, the first derivative equals the second derivative, and they both equal 6. Find the values of a, b, and c and sketch the curve. Okay, so I'll find A, B, and C, and then you guys can sketch the curve using the graphing calculator. Okay, so um, we have that for y equals x to the 4 plus ax squared plus bx. We have this point -1, comma -8. So that means that when x is -1, y equals -8. So -8 is equal to -1 to the 4 plus a times -1 squared plus b. Oh, and I forgot c. Yeah, plus c. Plus b times -1 plus c. So notice that we can expand this and rearrange it, and we end up with an equation. So this is going to be 1 positive. This is going to be plus a positive minus b plus c is equal to -8. Therefore, I'm going to write the equation up here to the right. It's going to be a minus b plus c is equal to -9. Okay. The other two equations we're going to get from the derivatives. So the first derivative is going to equal 4x cubed plus 2ax. Notice that we're treating a, b, and c as constants or as numbers. So plus 2ax plus b. But they tell us that when x is -1, the first derivative equals 6. So we can use that fact to find another equation. So we found the first equation here, and now we're going to find another equation. So when x is -1, notice I substitute x with -1, the derivative equals 6. The first derivative equals 6. So from here, we're going to find the second equation. So this is going to be -4 minus 2a plus b is equal to 6. Therefore, we can say then that minus 2a plus b is equal to 10. Okay, then the second derivative, right? So the second derivative would be then 12x squared plus 2a. And when x equals -1, this equals 6. So 12 times -1 squared plus 2a equals 6. So notice that we can solve here for a, because we're going to get the expression that 2a is equal to -6. Therefore, a is -3. So we found the value of a. b, we can find here because we have that a is -3. So notice that if I multiply -3 times -2, that's going to be 6. So 6 plus b equals 10. Therefore, b is equal to 4. So b is equal to 4. And then finally, we use the first one we found to find the value of c because we have that a is -3. So -3 minus 4, which is b, plus c is equal to -9. And then solving for c, we get that c is equal to -2. So that would be a, b, and c. Notice that then we can rewrite the equation as y equals -3, x to the 4 minus 3x squared. And then b was +4, so plus 4x, plus c, which is -2, so -2. So this equation is the one that you would graph with the GDC. Okay, so next we go with question number 10, and it says find any maxima, minima, or stationary points of inflection of the function f of x equals x cubed plus 3x minus 1 over x squared, stating with explanation the nature of each point. Sketch the curve indicating clearly what happens to x, or what happens as x goes into positive and negative infinity. Okay, so this question is probably not adequate for this chapter, but we're going to do it with what we know. So notice that we could rewrite f of x in a different way. We can say that f of x we could just divide each term, each one of these terms by x squared. So we can divide them by x squared. What are we going to get? Well, f of x would equal x plus 3 over x plus 3 over x minus 1 over x squared. And then it's much easier to find the derivative, because then the derivative would just equal 1 plus, actually minus, yeah. So 1 minus 3 over x squared plus, in this case, 2 over x cubed. So notice that all I'm doing is considering this to be 3 times x minus 1, and this will be minus x squared, right? So then when I subtract, or minus x to the minus 2, excuse me. So when I send this to multiply and then subtract 1, this is what I get over here, what I have to the right. Okay, so they want us to find stationary points. Now, stationary points would be, or would exist, when this equals 0. But in order to solve this, we need to have the same denominator. So the least common multiple is going to be x cubed, right? So this, we could rewrite this as x cubed minus 3x plus 2, and all of this over x cubed, and this equals 0. So remember, when you have a case like this doesn't really matter. You just have to solve for the top. But anyway, x cubed minus 3x plus 2 equals 0 is what would give us our stationary point. So the difficulty here is how do we factor this? What you do is that you grab this last term and think about all the numbers that can divide this. So 2 can be divided by plus minus 1, and it can also be divided by plus minus 2. So notice that if we plug in x equals 1, if x equals 1, then this equals 0, right? Because 1 minus 3 plus 2 would equal 0. So that means that x minus 1 is a factor. So divide this expression by x minus 1. We can do long division and divide it. And what we're going to get is that this divided by x minus 1 is going to equal x squared plus x minus 2. This still equals 0. And notice that this is easy to factor through inspection. And we're going to get x minus 1 times x minus 1 times x plus 2. So notice that I can write this again as x minus 1 squared times x plus 2 equals 0. And then that means that we have two critical points, which are going to be 1 and negative 2. So negative 2 and 1. Negative 2 and 1. Okay, so now what I want to do is do some tests to see if we have a maximum or a minimum, or if we have just a point of inflection. So with the first derivative, we need to test values that are before negative 2 and that are after negative 2, but before 1 and then after 1, right? Because we have to think in terms of infinity, positive infinity and negative infinity. Okay, it is also important to point out that we need to take into consideration 0, because 0 is where the function becomes undefined, as we can see here. All right, so we needed to ignore this to find the critical points, but we need to include it. We need to include 0 because it becomes undefined there. Okay, so what happens if we plug in, say, negative 3, right? A value that is less than negative 2. If we plug in negative 3 in the derivative, what are we going to get? If we plug in negative 3, we're going to get a positive value. You can test that for yourselves. Now, something between negative 2 and 0 would be negative 1. If we plug in negative 1, we're going to get a negative. Okay, so it means that this has to be a maximum because it's positive and then it starts going down. So this has to be a relative maximum. Then at 0 becomes undefined. What happens between 0 and 1? Say with 0.5. With 0.5, this is still going to be positive. You can test it out. And what happens with something greater than 1? Let's say 2. Well, this will be obviously positive as well. So that means that there's no change of sign. So this is probably a stationary point that is a point of inflection. We would still need to do the second derivative test to confirm that this is a point of inflection. I'll leave that to you. So we found that there is a relative maximum. So there's a relative maximum when x equals -2. So if we plug in -2, we're going to get -15/4. So that's going to be a relative maximum. Then a point of inflection when x equals 1. And if we plug in 1, we're going to get 3. So at 1, 3. But it says also what happens as x tends to infinity. What's going to happen to the graph as x tends to infinity. So remember that we rewrote this equation, and it's easier to see it this way. We rewrote it as f of x equals x plus 3 over x minus 1 over x squared. So what happens as x increases? But remember that if you have a limit as x approaches infinity for f of x, what would happen to this function? Well, this would tend to 0. This would also tend to 0. And this would tend to whatever x is. So x is infinite. Therefore, the function would tend to infinity. That means that it's going to go up. As x increases, the function will increase. What happens when we approach the other way, when we go to the left, when we go towards negative infinity? So this would approach 0 again. This would approach 0. And then this would approach negative infinity. So that means that the function itself would go to negative infinity. Now we're almost ready to graph this. The only thing that we have to take into account is the fact that we're going to have a line that is going to be a sort of asymptote. And why do I say that? Because notice that as you go into infinity, we're always going to have x remaining. Whatever the value of x is going to be where it tends to go. What do I mean by that? Well, if x is 1,000, right? Let's say x is 1,000, so this would be 1,000. Then this would be close to 0, so plus a little bit more than 0, minus another bit of 0. So it's going to be close to whatever value of x is. So that means that f of x equals x, f of x equals x is going to be a dotted line that we have to consider when thinking about this graph. So this is what the graph would look like. Notice that it's coming from negative infinity. So as x approaches infinity, the graph approaches negative infinity. Then here is a relative maximum at -2, -15/4. So this would be -15/4. Then notice that there was a change of sign, right? The slope was going up, it was positive, then it came back down. So that's how we knew it was a maximum or a relative maximum. It becomes undefined at x equals 0, then comes back up. And this is the point of inflection at 1, 3. So right here is the point of inflection of 1, 3. And notice that we have this, this line, y equals x, which works as an asymptote through which the graph goes through once, but then doesn't touch again. So finally, here we are in question number 11, and it says, for each graph function, sketch its derivative on a separate pair of axes. Do not use your GDC. So here they specify not to use the GDC. In all the previous questions, we were allowed to use the GDC. Remember, you can use the GDC unless otherwise specified. So it says, remember here to the left, remember that the derivative of an even function is odd, and the derivative of an odd function is even. This is very important. You guys know what even functions are and odd functions are. So for example, the semicircle, this is an even function. Why? Well, it's even because an even function is the one where you have a reflection across the y-axis. And so how do we do the graph of the derivative? So what I would suggest you do, first of all, is look for the points where the slope is 0. So here, the slope is 0 at this point. So obviously we have a slope at 0, 0, right? So because the derivative represents the slopes of the original function, 0, comma 0 would be a point on the derivative, okay? Then we have to look at the slopes. Notice that the slopes start very steep, so this would be undefined. Not interested in that, but we're interested in the fact that the slopes are steep, and then they start losing the steepness. So that means that it starts, and this is positive, right? It's going up because we read them from left to right. So that means that it starts positive, way up, and it comes down quickly, and goes through 0, comma 0. Now, because this is even, we know that the derivative has to be odd, and odd means that it has symmetry with respect to the origin. So if it looks that way here, we have to have a reflection of that below. So that's more or less the sketch of the derivative function of the semicircle. Now notice that after 0, comma 0, this would start the slope. Remember that we're thinking in terms of slope. So this starts going down, 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 and then down very quickly. Negative, negative, negative. Okay, the parabola for B, the parabola is also an even function, right? It has a reflection across or symmetry across the y-axis. And it also has here this slope of 0 when x equals 0. So that means that it also goes through the origin. So we can start by putting that point here. It definitely goes through the origin. Okay, let me get rid of this here for a second. It goes through the origin, we said. All right, so now let's take a look at the slopes. All we care about is the slopes. So positive, 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 and then 0, right? And then negative, 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 negative. So that means that it comes from the positives. Now this is a parabola, so the derivative of parabola has to be linear. So we can just draw a straight line. So we know that it has sort of steep, right? It's not that steep. It's kind of steep, right? So it comes from the positive because it has a positive slope, the parabola. So it comes from the positives, goes through 0, comma 0, and then goes through the negatives. So that's supposed to be a straight line, right? Okay, now let's look at letter C. So for letter C, we have an odd function. So that means that the derivative has to be even. In other words, it has to have symmetry with respect to the y-axis. Now, and because this looks like it might be, it has three intercepts, it looks like it's cubic. So the derivative would have to be a parabola, okay? But we're interested, first of all, in where the slope equals 0. So the slope equals 0 here and here, okay? So that means that it goes through 0, just let's say at like a value, it could be something like -3, and then again at +3. So notice that the slope starts negative. The slope is negative, 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 negative until it reaches this point. So that means that it comes down from the negative. It comes down from the negative and then reaches 0. And then here the slope becomes positive, positive, positive until it reaches 0 again. So that means that we have a curve that goes like that, right? Because it has to come back down to 0. So this represents those positive slopes that we would find in this part here. It gets down to 0, and then after that, after the 0 here, it goes negative. So this would go down to the negative. So, and then here we have a parabola, and it is symmetric with respect to the y-axis, or even. Okay, so here we have letters D and E, and that would be the last on the video. So look, first of all, again, look for where the slope of the original function is equal to 0. So this would be 0 here, it would be 0 here, it would be 0 here. Now I would recommend, because this one has more zeros, to name your places where it's 0. So let's suppose this is like -3, right? So -3. Then here we definitely know it's 0, comma 0. And then let's suppose this is 3 because it's an even function. Therefore, it's symmetric with respect to the y-axis. Now, remember that the rule says that if your original function is even, the derivative will be odd, right? Okay, so notice that the slope is negative, then it's 0, then positive, then 0 again, then negative, 0, and then positive. So we're going to use that as a guide to draw the derivative. So first of all, let's mark the points of the derivative where it will equal 0, right? So we said -3, which is more or less here. So let's mark there, -3. Then it goes positive. Then it goes to 0. Then it's negative. Then it's 0 again at x equals 3. And then positive, right? So we have a negative slope all the way until it's equal to 0 at x equals -3. That would be here. Then it's going to be positive for a bit until it gets to x equals 0. So it's going to be positive for a bit. It's going to go up and then back down. Sorry for the drawing, guys, but you get the idea. So it's going to be positive. So we got that positive. It goes to 0, and then it'll be negative. So it'll be negative for a little bit here. And then it's going to go back up because it has to go to 0 at 3. So notice that it's negative in this part. And then finally, positive slope from here on. So then positive, and because this one is odd, so it has to be symmetric with respect to the origin. So far so good. And then the other line would just be like that, and then we'd have symmetry here with respect to the origin. So this would be D. Now for E, we have a different thing because this one doesn't have any nice slopes that are equal to 0, because these little things here that are called cusps are not differentiable. In other words, this one doesn't have a slope of 0, and you can notice that you have a negative slope here and then immediately positive. There's no rest, there's no point on the graph where you have a nice and smooth point of inflection or a minimum or a maximum, right? Because you have cusps instead of the smooth stationary points. So this is a cusp, this is another cusp, this is another cusp, this is another cusp. So at these points, the derivative becomes undefined. Okay, so let's call these points just for the sake of a little guide. Let's say this is like -3, then let's suppose this is like -2. Actually, maybe let's say -2, -1, 0, 1, 2, and 3. So that's where it's going to be undefined, right? Okay, so let's just write those places where there will be no line. So we said, let's say -2, -1, 0. So -2, -1, 0, and then we said 1, 2, and 3. So here we have nothing on the graph at those points. So now let's look at where it's going to be positive. So it's going to be positive before, right? Before the first negative, which you said was -2. So let's say it's positive, and it's going to be constantly positive, right? Because this is a straight line going up, so you have a slope that doesn't change. So that means that you have a constant line coming from left to right that stops right there. And then, so we said this was -2. This is, I mean, we can't, it's not, we can't really say that it is -2, but I'm just using it as a guide, right? So positive, and then we have a negative slope, so it means it's going to be negative in this portion here, right? And then it's going to be positive again until it reaches 0 where it's undefined. And notice that I draw the line at the same height because all these slopes are equal. This slope is equal to this one, this is equal to this one, this is equal to this one. And the negatives are also equal. This one is negative, this one is negative, and this one is negative. So we go positive, negative, positive, and notice that it follows that pattern. So here it'll be negative again between 0 and 1, negative, and then between 1 and 2 it's going to be positive again, and then between, so this was 1, 2, then between 2 and 3 it's going to be negative. So between here and there, negative. Notice that this is also the same slope, so that's why we draw it at the same height. And then finally, after the 3, it continues to be positive. And this would be the graph of the derivative.